Welcome back, friends. Now that we are done with solving a partial differential equation of type 1, what was it? We just wrote a Lagrange's equation and we equated any two ratios and integrated it. Now, let us see what is type 2. In type 2, what will happen is that you won't be able to easily integrate two fractions. Let us say we have this dx by p equals to dy by q equals to dz by r. Okay. There will be a possibility that any of these ratios you will be able to integrate. Okay, but while integrating a second ratio or second equality, you will find some difficulties. In those cases, the solution that you found in one of the cases, like suppose you equated dx by p equals to dy by q and found some answer, the solution that you get in this particular equation will be directly used to get the second solution. Okay, so let us see how it is done. That is the type 2. One solution is used in another. How? Let us say we have an example. P plus 3q equal to 5z plus tan y minus 3x. And we are asked to find or solve this particular partial differential equation. Again, if we see, it is of the form P into P plus some Q into Q equal to this R. So its auxiliary equation can be written as dx by P equals to dy by Q equals to dz by R. Now, if you observe first two fractions, if I these ratios, if I equate them, these are easily integrable. So let us say dx by 1 equals to dy by 3. Cross multiplying, we get dy minus 3dx equal to 0. And once we integrate, it will be y minus 3x equals to c1. Let us say this is our equation 1. If you see this, the solution that we are getting y minus 3x equal to c1 and observe these auxiliary equations, we can easily say that we have y minus 3x here as well. And the second thing is that see, if we equate any of these ratios, if you equate first and third, this is function of dx, this is function of dz. hmm, But we will get y here, which we can't operate with. If we equate these two ratios, here we have dy, here we have dz. But again, we will here get x. Again, we can't operate. So in such cases, we will use the solution that we are getting, which is y minus 3x as c1. If I replace it here, see, let us take second and third ratio. Dy by 3 equals dz by second ratio was 5z plus tan. Here it was y minus 3x. Okay, but I have found it as c1. So I replaced y minus 3x with c1. We are left with 5z plus tan c1. Now if you observe, this is entirely a function of z and this is a constant. Okay, hence it is integrable. So if we integrate on both sides, we are left with y by 3 equals to 1 by 5. This is like integrating 1 by x, which will be log x. Okay, so log 5z plus tan c1 and a derivative of I here. Okay, plus some constant c2. If we rearrange it, we'll get it as 5y minus 3 log 5z plus tan c1 equals to c2. Now, once we get this particular equation, we will have to replace this particular c1 with the original one, which was 3y minus x. So, sorry, y minus 3x. Once we replace it here, we can write solution in the form of phi of y minus 3x equals to this particular function. Okay. See, earlier we wrote solution in the form of phi of c1 comma c2 equals to 0. Here as well we could write it, but just to show you in the other way how we could have written it, I have written it as c1 equals to phi of c2. Okay. This is an example of solving a partial differential equation of type 2, where we will be using one solution into another. Okay. Thank you.